Okay, I think we should start. Welcome everyone to this week's joint colloquium. We're very happy to have Joël Vernet from the European Southern Observatory visiting us this week. Joël is currently the ELT instrumentation scientist, but he also has, he's a scientist, astronomer by training, so he also has a science hat that he's not wearing this week, but you can also talk to him about science, and in particular, he's an expert in spectroscopic observations of high redshift AGN, specifically in terms of polarimetric observations. Joël received his PhD in 2001 from I hope I pronounce it correctly, Université Paris-Cité, so in Paris. He then moved on to a postdoc in Italy at INAF in Arcetri. And then in 2004, he became an ESO fellow, and he then never really left ESO. After his ESO fellowship, he became a project scientist first for X-Shooter, one of the instruments on the VLT, and then for Muse, for Harmony, which is one of the instruments that will go on the ELT, for Moons and Criris Plus. And since 2021, he's been acting as the ELT instrumentation scientist. We're very excited to have you here this week. Thank you for coming. And welcome to this talk, and looking forward to hearing more about the ELT. Thank you.
Thank you for the opportunities. I'm really happy to be here to show you the latest news about the ELT. So the goal today for me is to really explain you a little bit how the telescope works and what we are actually doing, the construction sites, because a lot is happening right now. And also to answer your questions, even during the talk, if something I say is not clear, don't hesitate to interrupt. I'll be happy to clarify so if anybody gets lost. So let's get started. So the ELT in a few numbers. I will show lots of numbers, but here just those numbers about 39-meter diameter primary, the largest infrared optical telescope ever built. 3,400 tons is the weight of the telescope alone itself, just a rotating part. The whole building has 100-meter base. The height of the dome is gigantic, 85-meter. One peculiarity of this telescope, also with respect to some others that are Team TGMT, so this one is really adaptive, thought as an adaptive telescope from the start. So, and it will host a suite of initially highly versatile instrument to cover most of the parameter space in terms of resolution, spatial, spectral, and wavelength, covering really a broad range of topics. Currently, it's under construction at full speed on Cerro Armazones, and also here in Europe, all over Europe, actually, with all the industrial partners that are in together with ESO in this endeavor, and also with all the institutes, astronomical institutes all over Europe. Two of them here with the Sternwarte, with MPIA, participating in the instruments. Overall cost, 1.3 billion euros. It's quite something. Not as expensive as JWST. We still have a factor of 10, so that's okay. Good. So maybe I wanted to, before going into the details of the telescope and everything, maybe take a second to step back. 400 years ago, Galileo, 4-centimeter lens, the first really astronomical instrument which revolutionized our view of the universe at the time. Get the Jupiter satellites and this. So that was at the time it was a revolution. Then here, the 1.8-meter telescope in 1845. It was really the first big telescope in a sense. Here we have a famous Hooker telescope, the 100-inch telescope at Mount Wilson, expansion of the universe, where Hubble made these discoveries. I could not go without mentioning the Hale telescope, the 5-meter. This is absolute marvel. You should, if you've never gone there, you should go there and try and observe. This is So this one was the 5 meter, was the biggest telescope for quite a while. Then there was the 6 meters, the Lensrud telescope. And then in 1993 came Keck with the 10 meter primary mirror. And of course, in 1998, the VLT. So I'm putting a picture of the VLT, and with the peculiarity of the VLT, it's an interferometer with a 100 meter base, which is has a unique suite of 12 instruments. So all of these projects, when they were built at the time when they were built, they were extremely difficult. They were at the limit of what we could do, and they revolutionized our view of the universe, all of them in their own way. The ELT is no different. I hope I will show you some of the challenges we are facing. This is really at the limit of what we can build, and we are facing lots of challenges right now, and I've tried to highlight them. So here, just for the historical perspective, you see this is aperture size versus time. Here we are over here with the 30-40 meter class telescopes, which I'm going to talk about. At ESO, at some point, we contemplated trying to break this law, go much faster, go to 100 meters. Some people here will remember the OWL project. We had the phase A study, but it was deemed too difficult, too expensive. And we went down to 42 meter, and then now today to 39. And believe me, it's complicated enough. Good. Just a size comparison to set the panorama. So here you see the 3 giant telescopes in the construction right now. This is the ELT, which is the biggest of all 3. For reference, you see the mirror size of the 4 VLTs. This is GTC. These are the 2 Kecks on top here. Take this opportunity to mention here, James Webb and Hubble Space Telescope. And so I did not mention space-based instrumentation here. It's not, no, but yes, also on a different track in terms of aperture versus time. Those ones are actually right now revolutionizing our view of the universe. Here on the bottom, you see the size comparison, and you see if you just look at here the size of the VLTs in the 4 VLTs on the platform compared to the size of the ELT dome, it's quite a sight. Go. So maybe some simple things I did. So if you've never thought about telescopes, maybe it's something you never even thought about. Why bigger? Bigger, of course, collecting surface, d squared, that's pretty obvious. But there is another aspect to it, is that the diffraction spot. So the PSF you get goes as 1 over d squared. So the surface of it, so it's a lambda over d, so the surface of your PSF, because it's 1 over d squared. So of course, the smaller the PSF, the finer the details, but also the higher the contrast over your background, you concentrate the light. And if you manage to reach the diffraction limit of your instrument, your sensitivity goes indeed as d to the 4th power. That assumes that you reach the diffraction limit. This is why the ELT is an adaptive telescope. All the instruments make use of advanced adaptive optics, and this is key to the project. When we will commission this telescope, and we will only be happy during the commissioning with our own diagnostic station. When we reach the diffraction limit, this is where we will tell the telescope is commissioned. So this is our aim. Good. One word about AO. If you've never heard about AO, I'm just mentioning for people who may not heard about this. If you have a source coming from the sky, of course, the turbulence distorts the wavefront. So what we do, we analyze part of the light with the wavefront sensor and compute with a complex control system what should be the deformation to deformable mirror in the pupil to apply to correct the wavefront and see an almost perfect image there. And so this acts in a closed loop, and we close the loop on our adaptive mirrors to have almost perfect images. Good. I will not talk too much about science drivers today. This is a big exercise we've done over the years together with the community in various groups, and this was basically 10, 15 years ago. And this really set the scene for this telescope. This is contrary to some other maybe domains of physics where you do an experiment to address one question. Here we are making one of this huge facility, but to address a whole range of topics for all fields of astrophysics, from solar system, exoplanets, to stellar physics, galaxy formation, and even cosmology. So really a broad range, and this is underlying to a lot of the work I'm doing, and we're doing also with the instruments, is to have always we have a very broad customer base, if I may say so, which sometimes have requirements that are contradictory, which is one of the difficulties we're often facing. So the site itself. So these telescopes will be, as you've heard, on Cerro Armazones in Chile. So here, this is the VLT currently in operation. Some people who've been there will recognize this Vista telescope. And the ELT is, let's say, across the road, 23 kilometers away. It will be operated still at the Paranal base camp here in the Residencia. And actually driving from one place to the other is quite a drive, about an hour or so. But during the night, our goal is to have a very limited staff over there and operate really everything from Paranal. So altitude of Paranal, the altitude of is slightly higher than the VLT at 3,000 meters. But one of the key for the choices of the site was to be close to the VLT infrastructure. We save a lot of money, and it's very convenient. Here, actually, at the moment, we're using already lots of the facilities at the base camp of Paranal. Of course, it's an excellent site, 300 clear nights, very stable atmosphere. So it's a site we know very well. It's very dry with minimum light pollution. Cerro Armazones is a little bit more windy than Paranal. So we have to, it's built in the design to cope with the very windy site, which is a bad thing because it shakes your telescope. It's also a good thing because it gets the flow of air into your telescope, which is very important. And of course, very high seismic activity. I will show you what some of the measures we have to take, similar to the VLT. We have to think about that at all times. The dome. So the dome itself, so made primarily to start with to protect the telescope from dust, because this is a windy place. It's in the middle of the desert, so there is a lot of dust. Also, the telescope, when it's open during the night, on the back side of the dome, you see there is a windshield, so we can rotate the dome so that we have protection to the telescope to avoid vibrations. There's also some windscreen also in front that we can deploy. So it's very important for that. Also for thermal conditioning, there's in the dome, there is a very big thermal conditioning system so that during the day, we adjust the temperature to be within 2 degrees of the outside air temperature when we open the dome. That is similar to the VLT. One thing that is very important and that we learn over the years with the different telescopes is to control the airflow around your telescope. When you put a big structure like this on top of a mountain, you of course disturb the airflow. And the thing you really want to avoid is to add turbulence. So here we've done, during the design of the dome, a lot of wind testing and adjustment of the shape of the dome, of the doors to avoid creating unwanted turbulence. The dome itself is a true monster, 6,100 tons rotating, so 80 meter high. The cathedral size, 88 meter rotating. It's rotating fast because it follows the telescope, of course, so that telescope can always see the stars. So when you're also close to zenith, of course, you rotate fast. It's expect to rotate up to 2 degrees per second, which is 5 kilometers per hour on the outer edge. So it really rotates fast. And in terms of also, so it's obviously it's a lot of power, but also it induces some safety issues. We need to be able to brake very fast this whole structure. So you can imagine the power of the brakes that you need when you rotate fast to stop it in a few meters. For just a size perspective, each of the doors that you see they're closed now weighs 600 tons. So here I showed a movie of what happens in the last year and a half. So we studied this movie, this time lapse starts in 2021 in September, and you will see here a year of civil engineering, of construction. So you can see all the scaffolding, all the concrete pouring, lots of activities up to basically arriving in November 2022, basically over Christmas. What was finished there was the foundation, the pier of the dome, so the whole structure onto which the dome is going to rotate. I'm happy to show this. So this is basically what happened since the hiatus of COVID. During COVID, we had to stop every construction. We had even to close all the contracts for constructions with the local company. So to start again, it was very difficult. We had to make new contracts and bring back a lot of people. It's been a very difficult time, but yeah, now construction is going full speed. So what you see here is the pier onto which the dome is going to rotate. I can show you here. So these are all the bogies onto which the dome is going to rotate that are now installed. Each of them is 27 tons. So it's a really massive pieces of engineering. And here, so this is big pieces of the dome rotation track that have been installed on March 15, so very recently. And 4 days later, all the rotation track was finished. And so these are the parts that this is going to rotate when we rotate the dome. I'll tell you also what is happening inside the dome just in a minute. Here, so once we have assembled all this track, the next step is the big Lego exercise. So you see this drone view here. These are all the pieces of the dome that already are in Chile. And what the teams are doing there is taking all the pieces and doing pre-assembly of big chunks of the dome, like you see here. And when those chunks are finished, they are brought to the telescope. This is the very first piece on the 19th of March that was drove up to the summit. And this very impressive tracks. I think I will go a bit faster on this one, as you see. So it's quite impressive, I would say. Going very slow, and there are many pieces to go up like this. And when this is done, these pieces, so this is one of them pulled up, and these pieces actually are bolted to the rotation track. And here, I don't know if you can see, but and then if you remember, so you really see the structure with the angle here of the dome being now put on. I think half of it. So this picture is from 3 days ago. I think half of the first ring, half of the first ring is already up. So yeah, on this picture, what you can expect. So this is, I'll say it again. This is a webcam. You can follow on the ESO website this webcam and see with a 2-3 days delay what's happening. I would encourage you to look at it. This is very nice. Now you've seen these big pieces. So the dome is going to take shape in very little time. So watch it. I think it's going to be quite interesting. The main structure. So what we call this let's say the telescope itself. In terms of movements, it's an as mount like the VLT and all the current big telescopes. So as I said before, 3,400 tons. They are holding no less than 700 tons of glass and mechanics and electronics. It stands on hydrostatic bearings, so it's on the oil bed. It's all resting on oil. It has an insane pointing accuracy of 0.3 arcsecond, 0.3 arcsecond. For a structure this size with all the flexures and things, it's very, very difficult to achieve. It's the to give an image is 30 centimeters with a 200 kilometers accuracy pointing. So it's quite something. And it's necessary. I mean, the reason we spec like this is it's necessary because when you do your adaptive optics, you want to be able to put your adaptive optic stars into your wavefront sensors, and the wavefront sensors will have a very limited field of view because of size of pixels, etc. I could explain why. So they will have a small field of view, and we have to put the stars in it. Otherwise, it will never work. We have very strong requirements on efficiency, new pointing, going from one part of the sky to the other in less than 5 minutes. So we want quick repointing. We have 2 Nasmith platforms, a CUDE room for the instruments, and I will talk more about this now. So all the units that are mounted into the structure, they're all alignable, focusable, deformable to compensate for all the external elements. So we have wind, temperature changes, gravity because the thing moves, in order to maintain at all times a perfect image quality. So here I'm showing where we are with the construction of the main structure. So what you see here is inside the dome. These things here are seismic isolation pads. I will show more of this on big concrete slabs. So these are the parts that you will never see again, of course, because so here detail on this slabs here, the absorbers here and the big pillars. So on top of that, we pour a slab. So this is the bottom slab of the telescope being built right now. With the rebars here, there's 1,000 tons of steel only on rebars just to build the bottom slab of the telescope. So this is the retaining wall, and though some of you are involved into the instruments, but here this is the intermediate ring where we will be able to circulate and move big parts of hardware to bring to the platforms. Also, the telescope parts are being built. This is the central azimuth track that goes, try to show right in the center. Here, this is the outer azimuth track. This also being built. It was pre-assembled in Europe. I don't think it's quite finished. I can't remember, but this is going to be just below the telescope on the outer parts, as I show here. What else? Oh, this one I like. This entire thing is actually the azimuth floor being pre-assembled in Italy. So this part here that is pre-assembled. So this is this part of the floor, and this is this part here that is pre-assembled. Look at the size when you will be walking. So it's kind of impressive when you'll be walking below the telescope. The main structure here, we have also some for steels we're building here. This is a part of the so you see the round shape. This is part of the telescope of the cradle that is being built right now. And this one I like. This is the M1 cell. So on top of this, the M1 segments will be attached. I'll talk about the M1 segments in a second. So this is a small part of the structure that is below here being put together right now. Of course, the telescope is optics and mechanics. So let's talk now about the big optics and the mechanics that are around this optics. So I've talked tons, so I will still talk tons. I've talked about things that were accuracies of millimeters or meters. Now we are going into nanometers. And so the telescope itself, so it's the design of the telescope is basically what we call a 3-mirror anastigmat, which is a design that is used now for most of the large projects. I think JWST is like this, LSST is also like this. So it has the advantage with the, because you know the VLT is only 2 powered surface. We have in the Richer Chrétien, we have 2. Now we have had the third one to have some larger field corrected. With the M3, we correct for the astigmatism as well, to allow to have a 10-minute field that we have. 10-minute field, diffraction limited. This is it was not easy. So we don't have, at the end, we have this number of mirrors for a good reason, still the same driver, aiming at the best image quality possible on, I wouldn't say large field, but for this size telescope, yes, it is a large field. This is folded with the two mirrors, absolutely essential mirrors, M4 and M5, M4 deformable mirror flat, M5 fast vibrating mirror for beam steering to send the light here to the platform where the sense instruments are. So path of the light goes on M1, M2 convex aspheric mirror. Then you have the M3 unique, also 4 meter class mirror. So you notice the light goes through M4 here. Here you have intermediate focus, which has lots of aberration because not yet corrected here. So you have basically no field and a lot of astigmatism here. So not really a good place for an instrument, but might be a good place for things like an ADC or things like some calibration unit as well, that we have some provision for putting something there. So it's also here, the size of the hole limits also the field. Then after M3, light goes on M4, M5, and to the instruments. So let's go through each of the mirrors and some of the challenges of each mirror, one after the other. 39-meter primary, 798 segments. They are all quasi-hexagonal. They're all different, yeah. I will talk about this difficulty later. It's a paraboloid, conic constants close to -1, almost -1. Order 6 symmetry. There are 6 families, so we cut them in corners. So 1, 2, 3, 4, 5, 6 families of 133 segments, which in each family, the 133 segments are all different. In total, we will produce one more family that is not shown here, another family of 133 segments to be able to maintain the mirrors. So we will every day replace 2 mirrors for cleaning, coating, and put the new ones in place so that there is never a hole in the mirror. So this means something I will not really detail, but we need to have a system to easily access the segments in the middle of the telescope during the day, extract them and replace by a new one, and be able to put it in with to tune it to the shape of the whole mirror in less than a few minutes, basically. So that is a real challenge. The M1 segment assembly. So these 798 segments, they are under, so first they are 5 centimeter thick, 1.4 meter across from tip to tip. And they are under a very complex high precision mechanics here, which I'm going to detail a little bit in the coming slides. So what you see basically, your segment, you have edge sensors to be able to sense what is the distance from each segment to its neighbors. We have segment support, that is a complex 27-point wiffle tree system, a fixed assembly, and very accurate positioning actuators. In total, so 4,600 M1 edge sensors, 931 segments, 2,400 positioning actuators, and all of the things we almost never talk about, all auxiliary sensors, mass dummies, cards for moving things around, stands, manipulator, phasing gun to put to align the segments. All of this, we have more than 10,000 components to procure in time and in good order. So M1 segments, you see some of them, they are 5 centimeter thick, 1.4 meter, made of zero-dur ceramics, cast here in mines by shot. So you see here the casting. It's quite nice. I think these were the first set of the production, and this is where we are today. Lots of boxes. We have 600 blanks produced, and so that was like a few days ago. I think there are probably another 27 that are in production right now. So it's really going full speed in the production of the mirrors, and as you can see, we already have lots of them. The supports, this 27, so we have there's something like three points, and each of these 3 points have 3-point support. So that's 9 times 3, 27. Wheel 3 is built by VDL. This to minimize all the deformations and the temperature effect on the mirrors to keep them in perfect shape at all times. The segments, they are positioned with some insane piece of engineering from coming from German industry, from PI. These actuators have a pitch of 15 millimeter and an accuracy of 2 nanometers, and this is crazy. So just a small image for you to visualize, because at least for me it's impossible to visualize. So if this 15 millimeter you compare them to a train on a 10-kilometer track, these actuators have to be faster than a fast-speed train, so 88 meters per second, very reactive. They have to be able to be super slow, like 2 millimeters per second, like a snail, and they have to position them. There would be a positioning at the equivalent of a 2 millimeter over 10 kilometer. This is what this 2 nanometer over 15 millimeter. So it's really a great piece of engineering, absolutely essential to get the perfect shape M1. And without this, it doesn't work. So the journey of the segments. So the segments, when they've been cast at shot, they are shipped to France in Poitiers at Safran-Réosc. They're polished, cut, then they put the assembly below, all the mechanics, and then they are finalized to a 15 nanometer RMS surface by iron beam figuring. A dedicated plant was built for that, and now this plant is now being filled with segments in production. When we are at full speed, we will produce 1 segment per day. Right now, we are not yet at full speed, still learning, debugging, correcting when needed. So at the moment, we're at 3 segments a week, but hopefully this is going to ramp up. And this is one of the segments finished and put on its assembly. So right now, so just to give you an idea of the progress, I wanted to show the blanks, 60%. All the fixed frame are produced, position actuators are produced, all edge sensors are there. Most of the supports are there. So once this is done, you can assemble the M1 assemblies and polish. So polishing, I think we have 27 of them completely finished. And the good news is that they are all much better than specified. I think we're between 5 and 10 nanometers RMS surface compared to 15, so really great. Good. M2, M3, these are big mirrors, 4-meter class. They were cast in 2017. M2 is very challenging. It's a highly aspherical, so this one is very difficult to make. It's the most convex mirror ever made. They're being polished. It's going to take still a while. I think they've gone through 4 rounds of polishing and another 7 are awaiting. The M2 and M3 cells is where all the mechanics to which the mirrors will be attached. They're being tested right now, and the electronics are being tuned. On this side, this is the M2 cell, and here it is the cell on which the M3 is going to be. And for those who are lost, this is, yes, the M2 cell will sit here 60 meters above the telescope. M4 deformable to correct the turbulence and all the residual aberrations. Maybe I should put it that the other way around, is to correct the residual aberrations and the turbulence, because without this M4 deformable mirror, the telescope would not reach its optimal image quality. It's 2.45 meter diameter, the largest deformable mirror made, 6 petals of 2 millimeter thick. This is here the inspection of one of those shells, very, very fragile, very difficult to make and not to break during the process. They will be magnetically, they will be actually levitating. They don't touch the surface, and they are actuated by more than 5,000 voice actuators. So this is an example of a finished shell with all the magnets on the back. And this is a very difficult element to make. So in order to have a perfect shape for this deformable mirror, we need a reference body, a reference surface, very accurate, and that is built in silicon carbide that is now finished. See some detail of the structure, or super lightweight structure, and all the strengthening, because it really needs to be super rigid. So this is there. All the actuators are there being built. These are the actuators that go on the back of the mirror. They are put into bricks, 170 bricks. They are all the bricks are done, and they're being now put onto the final system. And you see one of their challenges also in this deformable mirror, because there's a lot of energy dissipated, so it heats up very much. You need a very, very good cooling mechanism. Without this cooling, you would create heat into your light path, and then you would create turbulence, which is exactly what you want to correct for. That's really, the cooling is very challenging. And M5, finally, is a stabilizer mirror. This one is to correct wind shake and all the vibrations of the structure. Here you see the M5. So this is the dummy mirror of the M5 onto its cell. This one is probably the most, or at the moment is one of the most challenging part of the telescope to get to work. It's a elliptic mirror, 2.7 by 2.2 meter, super lightweight, extremely rigid. It weighs only 440 kilos, made also of silicon carbide. It will be vibrating at 10 hertz, so you don't want it to break, you don't want it to deform. This is, well, basically when we were trying to find a company to build them, they told us that we cannot do. So it was complicated. So here you see 6 petals of the mirror that have been produced. Now they're put together, and they will go. They've actually gone through into an oven to actually brace all the parts together. So this is coming along, but this afterwards has to be still polished, and the polishing of this material is very, very complicated. So this is coming along, but it's difficult. And before we go to the instrument, the prefocal stations. So just repeating the light path prefocal stations, we have 2 on each side. Prefocal stations here. So what we have in the prefocal stations, basically what you have is light analyzer to pick up the light from 3 stars on the outer edge of the field, to send commands to actuate all the 10,000 plus actuators of the real-time computer, to keep all the mirror in shape and to keep the image quality. And also on this here, you have, I don't know if you can see well here, the 6 mirror M6 that can send the light to either side of the platform of the prefocal station, directed to the different instruments on the platform. Prefocal station is coming along, it's being built. This one big piece that gives you an idea of the size of the whole thing. For those of you who have been at the VLT, have looked at through the equivalent for the VLT, the difference in sizes is massive. Prefocal station is coming along. This is built, actually the 2 are almost done. Here you see a piece of the sensor arm being there. They're also being built and coming along. The platform themselves, 29 meters across. I like to show this picture because that gives you an idea of the size. You can put an entire VLT on the platform, on each platform of the VLT if you wanted to do so. And finally, the instruments, last but not least. Without an instrument, telescope would be mostly useless. So here, just to reference, so you see the telescope, the platform. I'm highlighting here the prefocal station, and 3 of the instruments are represented. First light instrument here is Harmony, the near-infrared, optical near-infrared integral field spectrograph. Here you have Mikado, which is the camera, infrared camera, and also long-slit spectrograph. Here you see Morpheo, which is the multi-conjugated adaptive optics module to have adaptive diffraction limited images over the large field of Mikado. and also will serve later on a second, possibly a second instrument. And here in the back, you see METIS, which is the mid-infrared imager and spectrograph. Okay, briefly, the first generation of instruments that are part of the 1.3 billion budget that I was talking about. Initially, 3 instruments, as Harmony, METIS, and Mikado, together with Morpheo. They are funded in this first budget. Mosaic and Andes, which are 2 instruments, one is the Mosaic is a multi-object spectrograph, optical near infrared, and Andes, which is a large, very high resolution spectrograph, will be built later. They are just starting now. Some phase A studies was already successful, and it's will come to light, but a bit later. And since these instruments are built with all the institutes around Europe, which have accumulated a huge experience already with the VLT and other projects, so there's really a very big strength of our European community. The effort for the instrument in some of cost and FTEs is equivalent to the dome and main structure, or equivalent to the opto-mechanics. It's in the range of 300-ish millions plus. So for the effort will be, all the effort of the institute will be compensated in GTO nights. Just a panorama of, yeah, I got 1 minute. How much? 5 minutes, perfect. Just showing, instead of going into the detail of instruments, just wanted to show the parameter space, which come back to my slide on the science cases. So we're really serving a broad community with a very broad parameter space, which we're trying to fill as best as we can to attack as large as possible science topics. So here it's supposed to see the resolving power. So with the imagers being on the bottom at the lowest resolution, if you want, spectral resolution, and yes, wavelengths. So on the bottom you see the imager, Mikado, and METIS for the mid-infrared. If you move in resolution, here you have in yellow the IFU, which is a Harmony with different spectroscopic settings, different resolution, going from 3,000-ish to 17,000 here. Here you see the Mikado single slit. There's a mistake in this diagram. There should also be a box up here. METIS in the mid-infrared also does slit spectroscopy and also does higher resolution spectroscopy at 100,000-ish with its IFU. And that will come later, Mosaic, that will do multi-object spectroscopy over the optical up to the near-infrared, and Andes doing high resolution 100,000 spectroscopy for single objects from the optical to the near-infrared. You could also represent these instruments in different diagram. Here you see the field of view and the spatial resolution. So if we start with the Mikado, you see the 2 field of views. There's the low and high spatial resolution field of view. There's 20 or there's 20 arcseconds field. This is 50. Here you see Harmony with 4 different fields of view because it will have 4 different spatial resolutions. So you see it here, the IFU of METIS, a small field, the imaging, and here you see Mosaic here, which is the one that will exploit the largest field with a very large patch hole field to put fibers. And now you see, well, there's another way to see it. There's a summary of the capabilities of the different instruments. I don't think I will read through it. You can inform yourself. If I wanted to give a talk on instrumentation, it will be probably another 1 hour. I wanted to maybe to highlight here in terms of development. So all the instruments of first line had their phase A in 2009, 2010. Construction started in 2015, and they are currently going into the final design phase. METIS has just finished the final design. Now Mikado is almost finished, and Harmony and Morpheo are Harmony is about to start, and Morpheo will follow. This is this is the way it's going. So they are all trying to get to the telescope as soon as possible. So they're trying to speed up and to be sure that they won't miss their first light. And yeah, I think I'll stop here and wait for your questions. So yeah, construction is going at full speed. You can follow the progress on the on our website with the webcams if you want, and also with the news on the web pages. And yeah, if you have questions.
Thank you very much, Joël. I can add that the ELT website is beautifully made. It's very nice. There are also a couple of nice videos on there. Yes. Almost like James Bond trailer-like videos. So it's really worth going there and looking at some of the information. Thank you very much. Okay. We have time for some questions.
Yeah, just to kick off, a couple of questions actually. I may have just missed it, but what time would be the first light?
I didn't see it. I know I didn't.
Any
yes,
guesses?
At the moment, so we're on track for 2028 is the target date. But you know, as you know, we've been pushing that. We had Corona that stopped us completely. Took a year delay. And I would say now is the time when you bring pieces together. So, for instance, we had to. I think we can talk about it now. So we had some problems on the mounts of the M1 mirrors when we got the finished version. We said no, it's that the shape is not right of our mirrors. So we understood why, redesigned parts of the mounts, retrofitted all the ones that, and we're still retrofitting actually some of the parts that were made, and get it right. So things like this happen. So they've already happened. And I think it will happen again. That would be
yes,
amazing if it would not happen again. So
yes,
2028 is the set date.
Well, it is a bigger step actually on your log plots at the beginning of the historical development. My second question is actually in the design of the telescope and the structures, do you foresee extensions to 20 micron wavelength range? I mean, if in the infrared in the future, I'm thinking about sensitivity, high redshift research, and whether that's you see this as an instrument which will contribute to that in the era of JWST. Sorry, a telescope that will do that.
It's going far thermal is very difficult with this. So at the moment, SMET is the most far infrared of these instruments, but it's not impossible. Okay. It is not impossible. The design itself, for instance, which I think is good for it, is even for instance, when you vibrating the M5, you almost don't touch the pupil. So this is very important to get homogeneous background. So you have some optimization for the good thermal performance have been thought about, but probably could have been done even better. But it's a lot of compromises. It's as you can see, we can.
Yes,
so you're asking this question.
I apologize. I apologize for the question. I'm being much too greedy. I know this.
At the same time, I have with people who would ask the same question. So, how far in the blue have you thought about different coatings? How far in the blue can you go?
We're not caring about the blue, right?
You do, but some people do. So yeah. So that's part of all the compromises to trying to optimize. And,
thanks for the nice talk. I'm just wondering, with all this complexity, how much computing power are you going to need to run this monster with all the actuators, computing power?
So that's an interesting question. So I do not exactly know the answer to the questions, to this question. So I can give you maybe tomorrow or later tonight, because I can. So what I know is that when we started the project, we didn't have the computer power to run it. Now we do, but so I cannot tell you the number of cores and then what's that, but that I can find the information. I can tell you.
So I was wondering if you could say a few words about the lasers. So I understand that the ELT will be the full AO telescope, so the lasers will be constantly on, unlike
I had the slide on the lasers, and for time reasons, I removed this. So thank you. So yes, we'll have 6 lasers for laser gas sensing. It's very similar to what we have at the VLT UT4. They are the same lasers, exactly the same. I'm saying VLT UT4, but it's more than that, because now we have equipped all the VLTs with at least 1 laser for gravity plus. So we have already 4 plus 3, 7 on the mountain, with 6 for the ELT, which are coming along. And indeed, it is foreseen that we will do laser-assisted adaptive optics at almost all times. Yes.
Are there any contracts with the Chilean government regarding, I remember that when we were at VLT that there was, every time there was a plane approaching,
yeah, we're trying to
had to switch off the lasers and
trying to keep the airspace above those 2 telescopes as free as possible. Yes, but it's I think I don't know the details. I don't work on that in particular, but they are. I think the routes are updated on a regular basis, and then you have to stay. Hey, I'm there on a regular basis, because aircraft avoidance. We don't suffer so much of aircraft avoidance problems with the VLT UT4, as far as I know. Sometimes we have aircraft passing, switch off the laser, switch them on a few seconds after. We put on hold our AO loops, and the observations continue. What is a lot more complicated at the VLT is interference with other instruments. That is very good. That is complicated. Yes.
Just one more. I'm just wondering how much of your observing time will be ruined by satellite constellations?
I think we are not the most affected here, because as I was talking about large field, our large field is fairly small. So just to give you an example, in Harmony, the largest field at Harmony is a 9/6 of second. So the cross section is not very high. So we're not like wide field emitters where we'll suffer problems. But I still do expect that in the Mikado fields, in the one of interest, yeah, we'll get some trends.
So I was wondering, how often do we affected by earthquakes as a site, and how do ELT mirrors to deal with that earthquake?
So I've seen if we are taking all the precautions for the telescope not to break, the dome not to break, and everything. So all the mirror cells that I showed you have retained system, and systems that do not constrain too much the mirrors in case of a large acceleration. So mirrors are floating, but they are restrained from falling. The M4 with the levitating mirror also catches the shells in case of strong acceleration. So all of these are really thought about. In case of strong acceleration, all the mirror cells, they deal with protecting their own systems. Yes.
So if there are no other questions, then let's thank Joël again.